Hi everyone, so we're back again and we're actually going to get into kind of the nitty gritty here and talk about actually some brief introduction about polymers and specifically today we're going to get into kind of the basic structure configuration of polymers and soft matter. So what you're probably used to seeing if you've dealt with materials before and you think about metals or ceramics, you've probably seen these FCC crystals or BCC or simple cubic or hexagonal closed pack. What is this one? BCC. We know it's that iron, definitely at different temperatures. But anyways, you'll see kind of this periodic, this ordered array, this long-range order of metals and ceramics and other materials. But for polymers, we basically, if you look at the PDF, hopefully you remember this from material science, for metals, you see these spikes, long-range order. For polymers, you kind of see these undulations and they drop out. So we have short range order, but not long range order necessarily for polymeric materials because there are these long polymers, long materials, these long chains, and they kind of adopt these different arrangements. We're going to talk about it right now. So is actually in 1920, not too long ago, is actually Staudinger who first hypothesized that polymers were basically not composed of many molecules, but were composed of large, extremely large molecules containing sequences of simple chemical units. And he actually coined the term macromolecules. So you'll hear that term kind of interchangeably for polymers, macromolecules or polymers. Especially if you're kind of a bioengineer. Again, there's some nuances if you're a chemist as well. But again, we're not chemists, we're polymer physicists. You can just call them polymer, soft matter, whichever you want. So the key thing is that these polymers are basically composed of kind of this sequence of atoms called monomers. They're linked together with, usually with covalent bonds. There's some exotic ones, but that's the ones we're going to see, and usually they're organic also. So we're going to be dealing with carbon, hydrocarbons. These are organic molecules. And you could also monomers are generally, if we're just working with pure like synthetic polymers, so polystyrene, polyethylene, PVC, Kevlar, et cetera. You could also, sometimes they're called structural units if you're dealing with proteins and peptides. So if you have a protein or an amino acid, for example, that you're working with, sometimes instead of the monomer unit, they'll call it essentially a structural unit. So, for example, when you're working with those proteins, you might see kind of this generic structure, especially for amino acids. So proteins, again, naively are composed of amino acids. R1, this is just kind of some arbitrary functional unit. We're gonna see that in just a second. That's not an arrow. That's an sp4 bond. We'll go back to that in just a second. COH, and so this is kind of called a structural unit that's going to be composed of like one amino acid. So this R1 is just a placeholder. That's kind of like for whatever kind of really nuanced or functional chemistry that's attached to kind of this basic structural unit for amino acid. But we're getting a little ahead of ourselves. So let's focus on polymers, basically composed of monomers again, or a structural unit. And then certain cases, a repeat unit. So there's kind of a subtle but unique distinction between basically structural units and repeat units. So we'll get into that. Actually, the best way you can kind of visualize that is using an example. But I want to kind of point out here, you could see, so for polystyrene, for example, it's composed of the monomer is actually, looks a little bit like this. So we have our CH2, double bond to here, CH, and then we have our phenyl group. We'll look at that in just a second. Again, this course is not a polymer chemistry course. To do that, we'd spend a lot more time thinking or looking about these like functional units and kind of really learning these names. Again, this is a phenyl group, so we know that there's basically double bonds all around here. That's kind of the notation here. Again, we don't really need to know the chemistry behind it. We're going to learn in a bit later that this is a really rigid group, and that's going to affect a lot of the polymer properties. So don't worry too much about kind of drawing these chemical notations. When it's important, I'll let you know. But I want you to, again, the big focus here is the physical insight into how this affects polymer properties. So it's composed of this unit. We'll see that there's a certain chemistry that's going to break this bond and then create this long polymer chain here. And you can see that the abbreviation here, let me erase right here. The abbreviation for this polymer, you see how it's X or N number of units. So this number can vary between 10 to 100K. So large orders of magnitude difference. So we're looking at 10 to the 4 orders of magnitude difference, and that's going to really affect the properties. But we're getting a little bit ahead of ourselves. Let's go back to this idea of repeat unit and structural unit. So a repeat unit is a structural unit combination of structural units that repeats along a chain. So again, we usually call, basically in the parentheses, that's a monomer. So that is essentially usually a structural unit, but we'll see. Let's look at these 3 examples. So for polystyrene, how many structural units, how many repeat units, or do we have a repeat unit here? Well, let's look around here. So there's one structural unit, that is this guy, that's what is going to be repeated. So we have one structural unit there, and then it's repeated some number of times. So for polystyrene, we have one structural unit, because we have, again, in our parentheses here, it's going to be this CH2. That's kind of the structure of our polymer. And that's going to repeat. So this unit is going to repeat n number of times. So let's look at nylon 6,6. Unfortunately, we don't get to do interface polymerization and make nylon 6,6 in this course because of the remote teaching aspect of it, but I'll show you some cool YouTube videos, and then you probably have done this in Chem 24, and it probably didn't work. It never worked for me as a student either. Those demos always fail, but I actually think I found the solution and know how to do it well, and actually did it amazingly well. I know how to do it really well, so when this calms down, if you want to do some interface polymerization with me, we can go ahead and do that. Now, here, we can see in this polymer, there's 2 distinct structural units. So this structural unit and this structural unit. The actual process of this polymerization, and we'll get into this a little bit later, we're getting a little bit ahead of ourselves. The way you make this polymer is a condensation reaction. Let me do some quick polymer chemistry. 6, H2, then you add COH, and then CH2, 4 to COH. So you have basically these 2 structural units that you're combining to create this polymer. So here we have 2 structural units, 2 very distinct structural units, or monomers, you could call them. But again, there's only 1 repeat unit. So this repeats, this whole thing repeats over and over and over and over again. Now, if we have a block copolymer, especially a random block copolymer, there's A and B. So again, we have 2 distinct structural units, A and B. But is this ever repeating? No, it's random. So you could have a scenario where you have 2 distinct structural units, but no repeat units. So again, it's a subtle distinction, but again, I want you, if you're out in industry and you're giving talks, and if Professor Rubenstein is out there in your talk, you want to be very, very careful with your language so that you don't get yelled at. So that's kind of what we're talking about here. And we kind of just did our first polymer chemistry here to create that polymer. So when you link those structural units together, that is polymerization. So you link many monomers together, you make really, really long chains that are, very, very long in length, and that's how we polymerize or we make a polymer. So remember, this, or this right here, is not a polymer. It's just a structural unit. It's a monomer. But this big guy, the whole thing together, that's repeated n number of times, this guy, all of our kind of coiled polymer chains, those that are made up of, again, n equals 100K monomer units, that is our polymer. So that's what we kind of want to think about. So most of the times you'll see the monomer units are going to be composed of carbons. So typically you'll see kind of 4 carbons, the saturated hydrocarbons. Sometimes you'll see double or triple bonds. That's going to really affect essentially your mechanical properties and actually a lot of different properties of the polymer chain. One way you've probably seen this before when you deal with unsaturated hydrocarbons, especially with lipid bilayers. So it used to be you definitely don't want to eat like unsaturated fats or saturated fats. Or unsaturated fats, whatever. Anyways, there's a certain type of fat that basically these double bonds cause a kink in your lipid bilayer, and it basically makes it less fluid in order to move, and it really affects, again, properties of that lipid bilayer. So unsaturated or saturated hydrocarbons, unsaturated hydrocarbons will really cause some issues in there. So that's why we wanted to kind of deal with those guys. You probably saw that again. There was a big, at least when I was younger, this move from saturated fats to unsaturated fats, and it all has to deal with the fluidity of this lipid bilayer. But we'll talk about that a little bit later on. So, polymer chain, as we kind of mentioned previously, it could be composed of, if n is less than 100, we call that an oligomer. And then if N is, basically for a polymer, typically it's going to be between 10 and, let's say, 100K. So if N is around 10 to 100K, polymer. So generally speaking, again, these are really, really loose definitions here, but oligomer is like a waxy polymer. So wax is actually a polymer. But again, it's a short, polymer chain. And again, that's going to influence its TG, so the glass transition temperature. We'll talk a lot more about that later. Mechanical properties, melting temperatures, viscosity. It's going to change a lot of things about that kind of polymer. So again, typically you'll see that those polymers composed to 10 to 100K. Let me move my screen down here just a second. These are some just pure hydrocarbon chains that you might kind of come across. Again, I just want to introduce you. You don't have to memorize all these polymers. Please don't. But we just want to kind of introduce you and get you to start to see. And you'll see some pop up more than others. Polystyrene, polyethylene. Those are some that you might want to kind of memorize the structure. So they can be composed up to 10 to 100K. Polyethylene typically is 10 to the fourth. But again, it can change. You can deal with high density polyethylene, low density polyethylene, ultra high. So you can HDPE, LDPE, although this is more with branching, but we'll get to that later. So few branches, lots of branching. We'll see branching in just a second. And ultra high molecular weight polyethylene as well. So those are kind of again, you'll see some of the polymers that that'll occur here. There's also some really unique functional groups. So just like we kind of saw previously with, you could have basically some polymer. Let's say we have CH. This is polyethylene, but let's say we attach some really unique R group. We can make some of these R groups, or could essentially be right here. So to make polystyrene, we just attach this phenyl group where R is. So there's all these kind of unique functional groups that can be added. We're going to deal with a lot of them. Alcohols, amide linkages are really, really important in biology. That's kind of you've dealt with those before. In every peptide, every amino acid, there's that amide linkage that's extremely important. These guys we're going to start to kind of notice. We want to be on the lookout for polar molecules. So we know there's a difference in the electronegativity of C versus N, O, F, Cl, and we'll get to see again how that affects the polymer properties. But more on that a little bit later. We just kind of give you a brief refresher on kind of the structure of polymers, what can be added on, and kind of the unique aspects that we could expect to see a little bit later on in our course. But yeah, so those are functional groups. Then you could also get into some really, excuse me here. Let's go to our presentation. Same thing here, a little bit view zoomed out. There's some more phenyl groups. Again, these are all posted. And you can kind of see, so here's polyethylene, polypropylene. These are really common polymers. Here you can kind of see some really rigid polymers with these phenyl groups along the backbone. That's going to really change and increase. TG is going to skyrocket here. Again, we'll talk more about that later. You could see some kind of polar molecules right here on that kind of phenyl group. So there's really tons of polymers that you could deal with. Again, we're not going to memorize each of these, but we're going to look at the structure of that polymer. Again, looking at that angstrom level structure and how that affects meter scale properties. So that's kind of, again, what's the focus of this class? Scaling. Order of magnitude changes. So 10 to the, X number of changes. And then we also want to deal with time scales as well. How does time scale? That's kind of connected to scaling. Order of magnitude changes, and that's kind of the big, this hierarchical, these length scales as well. Time scales, length scales, scaling, everything that scales. So now let's go back. So those are just kind of some polymers that we can see. Now let's look at actually the structure of polymers. So polymers, again, a lot of times you'll see it as a random coiled chain. That's one of the popular ways that you can kind of visualize and look at polymers. But you may also want to investigate and look at, or there are a lot of polymers that are actually not this kind of random foil configuration. So let's kind of discuss and distinguish between what I like to call basically your polymer structure and your polymer configurations or conformations. So Right now, we're going to deal with polymer structure. So there's basically, we could look at kind of the atomic, that angstrom length scale structure, like the monomer structure, but we could also look at the polymer in general. So is the polymer linear? As we see here, it is linear for polyethylene, PMMA. That's a very common kind of polymer structure, or you'll often maybe even hear the term architecture. ARC. So polymer structure, polymer architecture, it can be linear, as you'll see here. It could be branch, cross-linked, ladder, comb, star, dendrimer. There's lots and lots and lots of different polymer architectures or different polymer structures that you're going to run across. And again, as you might expect, this polymer, or this linear polymer is going to behave much differently than this comb or the brush or the star architecture. And again, you could kind of create these different polymer changes. It's a little bit difficult, but we're going to talk about some strategies if you want to kind of obtain a certain property. So we're going to talk a lot about polymers, and again, this architecture can really change essentially the macroscopic organization of these polymers. So we're going to actually see that the polymers of, like, this is our A block, and then this is our B block. They can arrange into kind of different structures where, like, this is just A and then B, or you could have like these kind of cylinders of A and B, but more on that a lot later. Block of polymer can, basically architecture, or block of polymer phase diagrams can be developed depending on just by changing the length, basically of X of B and X of A. But much more on that a little bit later on. There's lots of different polymer architectures, and that's going to change, again, your mechanical and thermal and all these other properties, optical properties as well. There's also different polymer configurations. So each of these architectures, whether it be linear, whether it be star, block of polymer, they could adopt different configurations or conformations. Conformations. Sorry for the handwriting, but again, it's written down here somewhere. And again, we could change the conformation depending on temperature, environment, solvent, external stimuli. Those are our tools as, again, material scientists, as polymer physicists, that we could change that conformation. And that conformational change will affect properties. So one of the biggest things, there's this protein called von Willebrand factor, VWF. It's a globular protein that you can model as a polymer. So basically, it's kind of this random coil initially. So it's in your body. So your blood vessel, your VWF is just sitting there in your blood vessel right here. So blood vessel. When you get cut, the shear flows in that blood vessel increase. So you get lots of kind of shear flows in here. When that happens, that polymer goes from this globular state to an extended state. The extended state has like these binding sites. And the binding sites, what will happen is you have a cut, right, in your blood vessel. So there's a cut right here. Once this polymer becomes extended, those binding sites are exposed, and they bind here. Now, you might think the cool thing about von Willebrand factor is you might think that those binding interactions must be super strong to withstand the flow, right? But actually, they're really, really weak and really, really fast. So they're finding out more and more in biology that that's actually the case. Like, for the interactions are actually really, really weak but quick and fast, because they need to be dynamic and reconfigurable. But it's really counterintuitive, and if you're interested in talking more about that, we could speak on that another time. So conformations, again, different types. So you can have an extended, a coil, helixed, fringed micelle. We're going to be talking about these kind of folded, like lamella conformations in crystalline regions. Lamella, you could have a fringed micelle, all different types of kind of conformations that can come. And then again, that affects your material properties. So, to wrap up kind of on our polymer structure and conformations and architecture, and we want to kind of go broad and kind of classify our polymers into three groups. So either the polymers will be thermoplastics, thermosets, or elastomers. In this class, we're going to focus most on thermoplastics. So what is a thermoplastic? So a thermoplastic polymer is basically one that will soften and melt upon reheating. So you can melt, reform, and then you could melt, solidify, melt, kind of again and again, over and over and over. So it'll cool and harden, and basically as you increase the temperature and as you melt, so as you get above Tm, you're breaking intermolecular bonds. So these are not the covalent bonds along the backbone. These are bonds that we're going to see in the next lecture, the next video, that are essentially between, or inter is between the chains. So this is one polymer chain and it wraps around here. These are polymer interactions basically not within the backbone, not this guy. We're not breaking covalent bonds when we melt. We're breaking this other kind of interaction. This could be the van der Waals interaction, et cetera, et cetera. These are much, much weaker interactions, but more on that a little bit later. So as you heat up, you're going to pass the, you can melt, and if the polymer is basically semi-crystalline, some polymers are completely amorphous, in which case you'll go through the glass transition temperature. We're going to talk much, much, much more about this. But the glass transition temperature is basically you get enough thermal energy where you obtain and you see this kind of cooperative motion of 10 to hundreds of polymer repeat units. So basically, you move from a glassy state, it's like an actual glass. Like glass, if you heat it up, it goes through this similar transition to a more rubbery or fluid state. So many polymers, PVC, polyethylene, your trash bags, if you heat it up, you'll go through this transition of this glassy or rubbery state, and if you cool down, you go to kind of again that hard state. So we're going to talk a lot about that, and this glass transitions are super important. And it's an extremely unique property that's unique really only to kind of polymers. So you don't see metals and ceramics go through these things. So yeah, but thermosets are the ones that we're going to focus on the most because there's lots of kind of different processes you could do, extrusion, injection. They're really nice to work with. They're really ubiquitous, common, sorry, not thermosets, thermoplastics. Sorry about that. Thermoplastics we are going to work on the most. So that we are going to look at those and focus on them because those are the really unique properties that we're going to see. And again, they're more ubiquitous in terms of the materials that we're going to work with. And you can see here, thermoplastics can be either crystalline or amorphous. We're going to get into that a lot later. A thermoset is one that is chemically cross-linked. So these are permanent covalent cross-links between your chains. So you have a chain here, and then it is chemically cross-linked. Just like we saw for rubber, those disulfide bonds, those permanent chemical crosslinks, those are really they will not soften upon heating. So thermosets, one of the best examples I could give is like an epoxy. An epoxy, once it cures, you're done. You can't remelt and then reform that epoxy. It's done. And a thermoset is distinct because it has a high degree of cross-linking, so 10 to 50%. So those are thermosets. So once you heat it up, it doesn't go through that melting temperature or that TG. It just degrades. So it degrades at high temperature. So it's not this reversible transition. So again, vulcanized rubbers, epoxies, those are kind of the thermosets that you'll see commonly. An elastomer is kind of our last kind of section. So it's very similar to a thermoset polymer. It could have some degree of cross-linking. They could be permanent or physical cross-links, but I think the key distinction is they're not cross-linked to the degree of a thermoset. So they're not at this 10 to 50%. They're usually a little bit lower. And the cooler thing about the elastomers, they can be stretched greater than 10 times their original dimensions, and then they could recover that stress once it's relieved. So we're going to hopefully get into gels a little bit. It's always kind of a stretch at the end of the class because we cover a lot of materials, but elastomers and gels, they have very kind of unique and really fun properties that we can kind of explore. They basically, polymers can swell up to, 10 to hundreds and thousands of times their initial size. And it's because kind of some of these, interesting elastomeric properties. So yeah, that's about it for today. Next time we're going to get into kind of bonding, looking at, again, back into that angstrom level, see what intramolecular interactions are, intermolecular interactions, how do we kind of see how that can possibly affect your material properties, looking at isomeric states, and kind of lots of fun stuff. Hopefully it's a review a little bit from materials in the NGR 45. But yeah, so that's good. Please let me know if you have any questions, if you want some more examples or demos. But yeah, right now we're just looking at some classifications, and then we'll get into the nitty-gritty a little bit later. All right. Let me know if you have any questions again. And yeah, stay safe and healthy. And yeah, I'll see you all next time. Bye.